Okay, so let's plug in -2. What do I get? Awesome. Let's plug in -1. What do I get? Very good. Careful, when we plug in 0, we get, very good. When I plug in 1, when I plug in 4, again, I want to determine the end behavior. I'm going this way. 1/4, 1/2, 1, 2, 4, 8, 32, 64, 128. Where am I going? Very good. Now this way, 1/4, 1 divided by 8, by 16, by 32, by 64, 0. Y equals 0 this time is the horizontal asymptote at -infinity only. As you see, this is not a number. Okay, let's graph this function now. First ordered pair. Right, hard to plot. -1, 1/2, 0, 1, 1, 2, 2, 4, and so on and so forth. So this is 2 to the x. Can you say anything about this function? And I want you to go through these 8 properties that we mentioned for the other shape. Domain? Correct. So I'll just check for the other one. Range? Check. X-intercepts? None. Check. Y-intercept? Check. Is this function increasing or decreasing on all its domain? Yes, I'm going to put in brackets here. F is increasing when the base is greater than 1. Asymptotes. Right, correct. But this time at -infinity only. Is this function 1 to 1? Yes. Does it have an inverse? Check, check. Let's graph the inverse, although we don't even know what it is. Y equals x. Please give me several ordered pairs so I can plot this function now, the inverse of 2 to the x. Yes, 1/4 -2. Perfect. Perfect. Right. And so on and so forth. This is the inverse function. Is it clear that when the base is greater than 1, both the inverse, the function and the inverse are increasing functions? Is that clear? When the base is greater than 1, the function and the inverse are increasing. I have sometimes in the middle of the semester, students ask me, this is my joke of the day. Student asking me, can I still get an A in the class? Can I still get an A in the class? And I say, yes. As long as your grade moving on from now on will follow an exponential function with a base greater than 1. And they say, what? Sometimes. But students, once they understand the exponential function, they know what it means is the highest possible increase. Higher possible rate of increase. Okay, I would like to look at a transformation and then word problems. See how we apply such functions in real life situations. Okay, so let's say f of x equals -2 raised to x plus 1 and plus 4. We are asked to graph using transformations. And then we will determine the x and y intercepts algebraically. Okay, like before, we have to identify the base function. What function did I use to determine or create this one? Yes, 2 to the x. This was the base function that I used to create function f. Correct. Thank you, Amanda. Number 1. First transformation is on this function. Careful. In order of operations, x plus 1. 2 raised to x plus 1. What does the change of x into x plus 1 do to 2 to the x? Where does it move it? Careful, I'm changing x. Every time I'm changing x, it has to be this. To the left, 1. Very good. Perfect. Number 2 is the next transformation in line on number 1. I multiply all y values. It's outside. It doesn't touch x by negative 1. When I multiply the y values by negative 1, what do I do? Reflect with respect to the x-axis. Reflect with respect to the x-axis. And number 3 is the last transformation, which is basically on number 4. On number 2. Up 4. Very good. So let's graph all these. I'm going to graph 2 to the x. How do I graph it? Increasing or decreasing on all its domain? There are 2 shapes of the exponential. Increasing, very good. And where does it cross the y-axis? Always. The pure exponential function will always cross at 0, 1, no matter what the base. Good. Then you told me to shift this graph left 1. Where does my indicator point go? That's my indicator. That's what I want to use. Where does this go when I shift this red graph to the left 1? Very good. It goes right here. So this is 2 to x plus 1. Very good. What do I do to the green graph now? You already told me to reflect it. Give me the indicator point. Where does it go now? We're here with number 2. Exactly. Which point will that be? Perfect. Negative 1. Exactly. Negative 1, negative 1. So this is negative 2 to x plus 1. Final step. You already told me what to do, but please repeat. What do I have to do with this green graph? Up 4. Correct? Now let's identify the horizontal asymptote here. What is it? For 1, 2, 3. For these 3 graphs, there is a horizontal asymptote. Where is it? 0. Good. So when I shift the graph up 4, and it has a horizontal asymptote, what do I have to shift first? Correct. Where does the asymptote go? Exactly. 1, 2, 3, 4. I have to move the asymptote, of course, from y equals 0 to y equals 4. Now, please give me the indicator. Where do I take the indicator now? Yes. So at negative 1, comma, comma, exactly. 1, 2, 3, 4. It goes from negative 1 to positive 3. Ready? So here's the graph. This is the final graph. Final. F of x equals negative 2 raised to x plus 1 plus 4. Any questions on this? Now, remember what we said, that the range of the exponential function is 0 to infinity. But we are talking about the one without transformations. What is the range of this function? It's not 0 to infinity at all. What is the range of this, of the final function? Negative infinity to 4. So remember, when we talk about the base function, we mean no transformations, just simple function. For the range for this, negative infinity 4. And no pure exponential function has a horizontal asymptote of 4. But this is not a pure exponential. It has a lot of transformations on it. Any questions so far? Any questions? Okay, so let's look at a couple of applications before we move on. So this is 4.1. 4.1 on page 475. And I would like to talk about compound interest formulas. And if you'd like, problems 65 or 66. 65 has something about the population of India, and 66 has something about the explosion at the Chernobyl nuclear plant, and that was in 1986. Okay, so let's take a look. I'm sorry. You want the India? Very good. So let's look at the compound interest formulas, and then we're going to look at the population of India. A lot of real-life applications are modeled using exponential and log. And I think I gave you some examples. Bacteria grow exponentially, fast, very fast. Populations like rats, mice, rabbits, they all follow an exponential function. Earthquake intensity, a log function. Taking something like meat out of the oven, it decreases its temperature using a log function. A lot of applications. Okay, so let's look at compound interest formulas. They will be given to you. You do not have to memorize them. There are two kinds. One, continuously compound or recalculated. Continuously means every second. Continuously compound interest. The formula is A equals P E raised to power R times T, lowercase r times T. The interest compounded n times per year. N times per year. Compound interest. A different formula. A equals P, 1 plus R over N raised to NT. Now I will let you know what each and every letter represents. A represents the accumulated value.
The second one, is it LT or is it a 1? Yeah,
1. This is 1.
1.
This is 1. So A is the accumulated value. What does that mean? Let's say we go to a bank and we deposit money. 5 years later, we have an accumulated value. Yes?
After the E, what is that? N, R, pi?
This is N. This is N. This is lowercase r. This is lowercase r. This is T, and this is T. P, P, A, A.
Is it 1 plus or is
Yes.
that T? Okay.
1 plus. 1 plus. 1 plus r over N. I don't know what I'm doing today. Okay, so we deposit money into a bank account. 5 years later, we get back the accumulated value. We borrow money from a bank. This is what we have to pay back 5 years later. That's the accumulated value that we have to pay back. Okay, so it goes both ways. P is the principal. Whatever we take, whatever we borrow, or whatever we deposit, the principal. E is a number. It's Euler's number. Is approximately 2.71 and so on and so forth. It's an irrational number. I will show it to you in a minute in the graphing calculator. R, the lowercase r, annual interest rate. T, time in years. N, lowercase n, the number of times the interest is compounded per year. Number of times interest is recalculated, compounded per year. So now let's look at one problem. Let's say 53 on page 475. Any questions? Go ahead.
What does P say?
Principal.
No, what does E say?
Euler. It's a mathematician's name.
Oh, okay.
Euler.
Thank you.
Oh, sure.
Is it a number like pi?
It's an irrational number like pi. Yes. Yes.
Which is not the same as.
Okay, so let's take a look. We are told find the cumulative value of, so these formulas will be given to you, the compound, but you need to know what they mean and which one is used when and what each and every item represents. But you don't have to memorize the formula. Find the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5%. If the money is compounded semi-annually, quarterly, monthly, and continuously. Now let's identify what is given to us. What does 10,000 represent? Of course. What does 5 years represent? T, very good. What does 5.5% represent? Very good. Keep in mind, it cannot be used in percent. It has to be changed into decimal numbers. What does semi-annually mean? N equals twice. 2. Quarterly.
N equals 4.
Very good. And monthly.
N equals 12.
And here there is no N. For continuously compound interest, there is no N. It's done every second. Okay, so then here's the formula. Let's create the formula. A equals, the accumulated value will be, principal, you told me 10,000, in parentheses 1 plus R, 0.055, divided by X. I'm going to put in the graphing calculator. And because I put X because I don't have N in the calculator. And the power will be X times T, which is 5. 5X. So now let's go to our graphing calculators. And in Y equals at the top under the screen, under Y equals, so press on Y equals.
Where does the 5x come?
It's NT. I have 5, which is T, and I have N, which is X.
Oh, so for my, it says A equals T parentheses 1 plus R over N parentheses.
And the power is NT. And N is our X, and T is our 5. Good. So in Y equals, let's put in this function, 10,000.
Is it in parentheses?
Left parenthesis. No, 10,000 can stay outside. No parenthesis for 10,000. So 10,000 left parenthesis, 1 plus 0.055 divided by X. Close the parenthesis. Don't forget to put a caret now for the power. And in parentheses, 5X. So 10,000 in parentheses 1 plus 0.055 divided by X, everything raised to power 5X. Now let's go to second and table. I forgot to check. Sorry, I have to check this all the time. It's yes, it goes back to default for me. Make sure you have the independent variable in the ask mode. Independent variable in the ask mode. Go to second and table set. Second and table set. Wendy? Second and table set.
Okay.
And scroll down and highlight ask for independent.
Okay.
And press enter, in other words. And now go back to second and table. And we're putting in, as we know, 2, 4, and 12. 2, enter, 4, enter, 12, enter. And I got the answer. But please go up and to the right to get the decimal digits. Okay? So the answer for this is 13,116.51 cents. So A of 2, 13,116.51. You're going to see what I'm writing in here in a second. A of 4. Any questions, please? Any questions?
Are we putting in what you have under Y1 or under the bigger one? Are we rounding?
No, that's why I highlight so I can see it here. Yes. Yes, we need 2 decimal digits for our money. 13140.67. So now I am rounding. And the other one is A of 12. Let's check. Go down. 13157.04. So, A of 2, A of 2, A of 4, 4 times a year, and A of 12. Now, for continuously compound interest, I have to create a new formula. So that will be 10,000, and without parentheses, sorry, I just got in the habit of writing. E to R 0.055 multiplied by 5. I'm going to delete the parenthesis.
So like the 10,000 principal, right?
Yes, P E to RT. So this is, go back to the calculator, please. We cannot, there is no need to use the table for this one because I don't have multiple, I just have only one calculation. 10,000. Here's where E is. Very important right here. See this key? E to the X and LN. They're on the same key. They are in a perfect relationship. They're very good friends. Second and E to the X, parentheses, 0.055 multiplied by 5, close the parenthesis and enter. So for continuous compound interest, we get 13165.31.
Where did you put that? No, where is that?
E, it's in the same key with LN, but you have to use the second key.
Oh, you know,
Oh, okay.
Better? Is this okay?
10,000.
And this is compounding continuously?
Compounding continues every second. That's what continuous means.
Oh, that's the first one.
All the time. Yes.
Okay.
So now let's look at the word problem about India's population. Let's read it. India is currently one of the world's fastest growing countries. By 2040, the population of India will be larger than the population of China. By 2050, nearly 1/3 of the world's population will live in these 2 countries alone. 2 countries alone, 1/3 of the globe. The exponential function f of x, so this is problem 65 on page 475. We are given f of x equals 574 multiplied by 1.026 raised to the x power.
Can you put it back on the projector, please?
Of course. Sorry. So 65 on page 475. India is currently, okay. So models the population of India, f of x in millions. X is the number of years after 1974. So what does 1974 represent? X equals? X being the number of years after 1974. What does 1974 represent? X equals 0. Right? Number of years after 1974 means 1974 represents x equals 0. Is that clear? Okay, part A. Substitute 0 for x, and without using a calculator, find India's population in 1974. That's part A. So f of 0, how much is a number that is not 0 raised to 0? So then 574 million. Part B. I'm going to ask, do you think that this function is an increasing function or a decreasing function?
Increasing.
Why?
Because of your population.
Because the base of the exponential function is greater than 1. We know that. We graphed two shapes. We graphed one shape that has base less than 1, that looks like this, and we graphed another base that has another exponential function that looks like this. And that base is more than 1, therefore it's increasing. Good. Part B, substitute 27 for x and use a calculator to find India's population to the nearest million in the year 2001. Part C, I'm just going to read C, D, so I can put the book away. Find India's population to the nearest million in the year 2028. Find India's population to the nearest million in the year 2055. And part E, what appears to be happening to India's population every 27 years? Okay. So now I can get rid of the book. So, x equals 0. In 1974, India had 574 million people. Okay. In part B, we're asked to find f of 27. What does f of 27 represent? If we add 27 years to 1974, what do we get? 2001. So in 2001, x equals 27. Let's go back to our graphing calculators. In y equals, clear. And let's put in this function, 574, parentheses, 1.026, close the parentheses, caret. You may not need parentheses, but you know me already. I have to have parentheses. They're my best friends. No, you are my best friend. Okay, so second and table, and I plug in 27. So 1 billion, right? It was millions. 1,147,900,000. So 1,147,900,000 millions if you want, but that's billions. Million. Okay, now we want in the year 2028. That was the next question.
Wait,
Say it again.
what was the 2001 for?
27 years since 1974. But now we want to determine the India's population in 2028. What do I have to plug in this time?
54.
So I have to, because it was 27 plus 27. Very good. So that's what I want, 54. So 2295.5. Okay. Finally, for 2055, what do I plug in for that?
81.
Because it's 54 plus 27, 81. So let's plug in 81. 4590.4. 4 billion people. 4590.4 million. And now the question. What appears to be happening with India's population according to the model? According to the model, every 27 years. It doubles. It doubles. Assuming the model is true. Moving forward. Very good. Any questions for me? Any questions? Okay, so we can move on. The next, before I mention, not before I mention, there are two special exponential functions. So special that they have their own key in the graphing calculator. Two special exponential functions. One is called common. The other one is called natural. Common exponential function, natural exponential function. The common exponential function has base 10. The natural exponential function has base e, Euler's number. So this one looks, can anyone tell us how will the common exponential function with the base 10 will look like? That's it. Awesome. Now this one has a special notation because it's e, right? E to the x. So the natural exponential function is e to the x. The common exponential function is 10 to the x. And now we can look at logarithmic functions. And yes, in case you're wondering, there will be a special function called common log with base 10. There will be a special function called natural log with base e. In a minute, we'll list them. Okay, we do know two shapes already. We graphed them a few minutes ago. Here's one. And here's the other. These are the logarithmic functions that we graphed a few minutes ago. I can go back if I find my previous page, as I did. Okay. And this one. So can anyone tell us what is the base in this case? Is it greater than 1 or less than 1? Yes, because it's a decreasing function. And obviously this is greater than 1. Here's the notation. The notation is a little bit intimidating. Please do not be intimidated by it. So if this is the inverse function of the base 1/2, this will be log base 1/2 of x. So this is f of x, log base 1/2 of x, log base 1/2 of x. Can anyone give us the name of this one? F of x equals log base, there is no base 1. There is not 0, 1, or negative. It was not, we did not graph e yet. 2. Log base 2 of x. Okay, what can we say about the log function? Domain, range, increasing, decreasing, and so on and so forth. What is the domain? Yeah. Careful with this function. It's not friendly in that sense, that it's defined everywhere and I don't have to worry about it. What about the range? Of course. It must be the domain of the exponential function. Range, all the numbers. X-intercept. X-intercept. Very good. Because the exponential had 0, 1. This will have 1, 0. Awesome. Asymptotes. X equals 0. Very good. X equals 0 is the vertical asymptote. This one. Very good. Is it increasing or decreasing? Let's look at the first function. So f decreasing for a base between 0 and 1, but f increasing for a base greater than 1. So these go together. Is it 1 to 1? By the horizontal line test, is 1 to 1. Doesn't have an inverse. Yes. Of course it has an inverse. We already graphed the inverse half an hour ago. Okay. Now you should say, and I'm sure you're thinking it, but you're not saying it, show me that this function is the inverse of the exponential. You haven't shown that, and I haven't yet. Before I show you how this works, we have to go through and discuss the most very, very, very important concept. I would consider the most important concept in this section, in this chapter actually, in chapter 4. The most important concept in this chapter is any log or logarithmic, in short, log equation can be replaced. If you want to write converted into, that's fine too, by an exponential equation, comma, and vice versa. This is the most important concept, in my opinion. Well, this is in plain English, but how do I write this in mathematical terms? Here's how I write this. Log base A of x is a number y. This is a log equation. This is equivalent to, and this is the double equivalency symbol, which means from here I can get here, and from here I can get here. Double equivalency. From left I can get to the right, from right I can get to the left. So please pay attention how we change this into an exponential notation. This concept is very important. The base, counterclockwise, the base raised to y power equals x. The base raised to y power equals x. And this is an exponential equation. And I just realized that I mentioned when we use transformations, my apologies, we'll go back to it right now after we discuss this. When we graph this using transformations, I said after we graph it using transformations, I would like to determine the x and y intercepts algebraically. So we're going to do that in a minute. I forgot. Okay, the most important concept. Log base A of x is y can be changed into a raised to power y equals x. Okay, let me show you the mechanism. Let me try to convince you. Give me any exponential function you can think of. You don't have to choose the ones that we looked at, but don't use a huge base because it will become more arithmetic than concept. And give me 3 numbers. One should be 0, one should be positive, and one should be negative. Very good. Let's say 4 to make it, okay, different. So now please give me any exponential function you want to work with.
Can you look it up a little?
Any pure exponential function, no transformations, just a simple exponential function. 4 raised to the x. Not 4x, but 4 raised to the x. Perfect. Awesome. So how much is y when I raise 4 to negative 2? Careful. A negative power does not mean a negative number as the result. 1 over 16. Do you all agree, Wendy? Is that clear?
Yes.
4 to negative 2 is 1 over 4 squared. Good. Now let's plug in 0, please.
4.
Perfect, always. Let's plug in 4. How much?
256.
Perfect. So now this is clear. No questions, I'm assuming here. But I have the obligation now to show you that the inverse function, which is log base, say it again. It must be the same base, awesome, of x, is indeed the inverse function of this. I have not shown you that. And you should not trust anything before I show you. So how will I show you? Here's what I'm going to do. I'm going to apply this function to 1 over 16. And if the answer is not, then I'm not telling you the truth. I will apply this function to 1. And if the answer is not, then this is not the inverse function. And I will apply this function to 256. And if the answer is not 4, then this is not the inverse function. Okay, ready? So, log base 4 of 1 over 16. I have no idea what it is, but this is what type of equation? Very good. I know how to change it into an exponential. How do I change this into an exponential equation? Using the most important concept in this chapter.
4 raised to x.
Yes, 4 raised to whatever equals 1 over 16. What will that number be? And it must be a negative number. It must be negative 2. So 4 raised to negative 2 equals 1 over 16. So I hope I convinced you that when I apply log to 1 over 16, we return negative 2. So what will you say for now that we observed? That log is a power. What power? The power I raised 4 to get 1 over 16. And what is that power? Negative 2. So log is a power. The exponential is an exponential equation function. So now I'm going to apply log base 4 to 1. Let's see what we get. Log base 4 of 1, I have no clue, but I know that this is equivalent to an exponential equation. Which exponential equation?
4 raised to whatever.
Very good. Now let's think. I raise 4 to only one number to get 1. 0. So this must be 0. So I go back and I'll say, oh, okay. When I apply log to 1, it returns 0. Of course, the other one will work, but let's do the last one as well. Log base 4 of 256, unknown number, but I know how to change this into an exponential equation. 4 raised to, I have no idea, equals 256, and the answer must be 4. So this is how the mechanism works. How I show that indeed log is the inverse of the exponential. So now let's look at, I will not forget to go back and determine that algebraically, x and y intercepts, but 10 to the x is the common, so this is f of x, 10 to the x, common exponential function. Corresponding to this, f inverse will be log x. And this is common log function. You can say, I don't see the base. By convention, if you look at your calculators, let's look here. By convention, you will see log. Right here, log. And you see it doesn't pop up with a base. So that's the key for common log. When we don't see a base is 10. Okay? Now the other one, since I have the calculator up, the other one is the next key, ln. ln, natural log. And this will be the corresponding or the inverse function of e to the x. So this is common log function, and the other one will be natural log function. So when f of x is e to the x, and this is natural exponential that we looked at a minute ago, and f inverse, it's not written log, but ln x. Again, you can say, I don't see a base. If you don't see a base and you see ln, the base is e. So this is natural log function. Natural log function. Any questions?